Part of our sequences and series content is going to involve this thing known as sigma notation. So you've had some exposure to the Greek alphabet, especially when we worked with trigonometry. You would have seen angles like theta and beta and alpha. Those are all letters of the Greek alphabet, and they sort of represent variables in our trigonometry. And so we encounter another one now known as sigma, which you may have seen when you did statistics in grade 11. But if you haven't seen it, let's have a look. This sign here is the Greek letter sigma, and it means sum of. So if you're looking at sequences and series, you are looking at the S formulae and not the ones that go with T. Okay, so something like this represents something very specific. So it means the sum of these terms, okay, and then you substitute in a value. So in this case, we would start at 1. This is always our starting point down here. And you would end with the value on top. So that's our end point. And you would basically substitute and add each of those terms together until you finally arrived at an answer. So in other words, the sum to end terms starting at 1 of tk is going to equal term 1. I start by substituting in a 1, plus term 2, I'll sub in the next number here, a 2, plus term 3, plus I'll go all the way until I reach term n, that final one there at the top. Okay, so now this is a very theoretical understanding, but I think once you see it in practice, it'll make a lot more sense. So let's look at this example. We need to calculate the value of 2k minus 1, the sum of it, if we start by substituting in for k is equal to 1, and then our final term, we substitute k is equal to 6. So we can simply expand this, and we can now sub in. So 2 times 1 minus 1, that's our first term, plus 2 times 2 minus 1, that's our second term, 2 times 3 minus 1, 2 times 4 minus 1, 2 times 5 minus 1, and finally 2 times 6 minus 1, because the value on top of the sigma notation is 6. That would be my last term. Okay, and then what you can do is you can just work these out. So 2 times 1 is 2, 2 minus 1 is 1, plus this is going to give us 4. 4 minus 1 is 3. Plus, this is going to give us 6 minus 1. Plus, 8 minus 1. Plus, 10 minus 1. And finally, 12 minus 1. And you can type that into your calculator and come to an answer. So just to recap, when you see the sigma notation sign, it means the sum of. In other words, you need to add the terms together. They will usually give you a general term to work with. You start by substituting in the value listed underneath the sigma notation, and the value on top is the last one that you substitute in. And once you've expanded it, you will be able to add your terms together. Okay, so that's the foundation. Now we're ready to build on it. So here we have 2 examples. Calculate the sum of, the minute I see that sigma sign, I know that's what they mean, the sum of this general term. If we substitute in for I, we start at 1 and we go all the way up to infinity. Okay, so in the previous one, we literally could stop at 6, but now that we're dealing with infinity, we're going to have to think carefully about how we can apply our knowledge of the sums of geometric series. Okay, whenever I get a sigma notation, I start by working out the first couple of terms, and that always helps me to determine, am I working with an arithmetic or a geometric series? Okay, in this instance, let's substitute in. So we're going to start with 1. So 10 to the power of 2 minus 1 is going to be 10 to the power of 1. So our first term there is just going to be 10 plus. Now we're going to have 10 to the power of 2 minus 2. So that's 10 to the power of 0, which is going to equal 1, because anything to the power of 0 is 1. Then we've got 10 to the power of 2 minus 3. So it's 10 to the power of minus 1. So that's going to be 1 over 10. Plus, let's do one more. So we've done T1, T2, T3. Let's do T4. So 10 to the power of 2 minus 4, that's going to give us minus 2. So that's going to be 1 over 10 squared, or 1 over 100. Okay, now we have a look. Is this a linear or an arithmetic sequence? Or are we dealing with a quadratic? Or do we have a common ratio? Is this a geometric series? Okay, and in this case, I think it's easy enough to see that there's no constant difference here. So there probably is a common ratio. Let's check it out. What's term 2 divided by term 1? That's going to be 1 over 10. And then we compare that and we say, okay, what's term 3 divided by term 2? And we see, do we get the same answer? So term 3 is 1 over 10. And we want to divide that by 1. What happens if you divide anything by 1? You get 1 over 10. So there we have it. We've got an R value of 1 over 10. Okay, now because I cannot just keep working out terms for an infinite amount of time, I'm going to have to rely on my formula. Okay, so the minute we saw this sigma sign, we knew that we were dealing with sum. And now that we've worked out an R value, we know we are dealing with the sum of a geometric series. So let's have a look at the formula sheet. And what you'll see on your formula sheet is you've got two. You've got an Sn equals, and then you've got an S infinity equals. Okay, and we're going to work with that infinity one because this series is going up to infinity. So the sum to infinity is equal to A over 1 minus R. Okay, and that only works when R is between minus 1 and 1. And if you have a look at the R value that we're dealing with, it's 1 over 10. It definitely fits well between minus 1 and 1. So now we can substitute in. So we can say the sum to infinity is equal to A, my first term there, 10, over 1 minus the R value there is 1 over 10. And then you can pop that onto your calculator, and it gives you an answer of 100 over 9. And then you just need to check the instructions on your test paper, and generally they want things to 2 decimal places. So 11,11 would be the sum to infinity there of this series in sigma notation. Okay, let's have a look at this next one. This one looks a bit more straightforward, from 8 to 22. If I was really committed, I could literally sub in 8, 9, 10, 11, 12, all the way up to 22. Sure, it'll get long, but I will be able to get an answer like that. But let's try this same approach where we expand and we figure out the first few terms, and then we have a look, are we dealing with an arithmetic or geometric or a quadratic series, and then we see if we can use one of the formulae on our formula sheet. So what we're going to do is we're going to write, starting with 8, we're going to substitute in an 8. Our next term, substitute 9, 10, etc. And we can see that this needs to stop here at 22. So let's work each of those out so that we have a clearer sequence to work with. Right, so there we have it, and I got all negative answers. And so what I've done, just to avoid the confusion with the plus and the minus, is I've put each of the terms in brackets. Okay, just to help me see. So the sequence behind this series is minus 38, minus 43, minus 48, etc. And so if you look at that closely, you will see in each instance you are subtracting another 5. So that makes this an arithmetic series. Okay, it's a series because we have this sum, the sigma notation given to us. So we hit our formula sheet and we see what is the sum of an arithmetic series. Okay, so we've got n over 2 brackets 2a plus n minus 1d. Okay, and then there's the other one with the last term, but that one is not given to us on the formula sheet. We would have to learn it. Either way, no matter which one you substitute into, you should end up with the same answer. Okay, but the question now, grade 12s, is what do we substitute in for n? A is our first term. That's going to be minus 38. Let's write that down. A is equal to minus 38. D we've known to be minus 5 because we worked that out. And then we need to know n is equal to something. Okay, and whenever we're dealing with sigma notation, there is a way that we work out n, and it's very important that you remember this. So n is equal to the upper number minus the lower number plus 1. So in other words, if I want to work out the n value here of this sigma notation, I'm going to say n is equal to the value above the sigma notation is 22 minus the lower number is 8 plus 1. And so that takes me to 15 terms. And now that I have that, I can substitute in and determine the sum. All right, I'm going to use this formula here because I have the first term and I have the last term. It's going to be easy enough to solve that. So sum of 15 terms now, because we've worked out n, is equal to n over 2, 15 over 2 times by our first term there is minus 38 plus our last term there minus 108. Okay, and we can type that on our calculators, which gives us a sum of minus 1095. Now we could also be given a situation in reverse. They give us a series and they ask us to represent it in sigma notation. So if we think back, we understand that sigma notation needs to have a general term, it needs to have a starting point, and it needs to have an end point, the last term number there. Okay, so those are the things we need. Let's start out by just working out this Tn. Okay, so we're going to look at our series that they've given us here, and we're going to decide, is it arithmetic, is it geometric, is it quadratic? Okay, in this case, plus 3, it seems to be an arithmetic series. So we head to our formula sheet and we say, we know that an arithmetic series Tn is equal to a plus n minus 1 multiplied by d. And in this instance, I need to know what a is, so my a value, and the d value there is the constant difference. So we can substitute that in, and that will give us the general term. So 4 plus n minus 1 multiplied by 3, and that is going to simplify, and we will end up with 3n plus 1 as our general term. Okay, now we will always start with term 1. So the underneath number is in place. Let's start putting this together. We know our general term now is 3n plus 1. We've calculated it. And we know that we're going to start with term 1 to get our a value there. But we do need to figure out where we end off. Okay, so let's look at what we've been given that we haven't utilized yet. And that's the fact that this goes all the way up to 88. So I can use this general term that I've just calculated, and I can say which term number is equal to 88. So if we say 3n plus 1 equals 88, and then we solve, it'll help us determine what we substituted in there. So t what is equal to 88. So let's do that. 3n is equal then to 87. And if I divide both sides by 3, I end up with n is equal to 29. And that is the final piece in my puzzle. That helps me to say the last value that I substitute in is 29. And so there we've done it, grade 12s. We have taken a series and we have compacted it into sigma notation. We have shown that we are adding all the terms that have this general term starting with 1 and ending with 29. Let's have a look at another one. So here we are given again the series, and we need to, step 1, figure out, is this arithmetic or geometric or quadratic? Okay, having a look at it, what am I doing each time? I am definitely not seeing a constant difference. So let's try and figure out if there's a ratio here. So we'll take term 2 divided by term 1, so that's a half, divided by 1, which is a half. Okay, let's see if it's the same with term 3 divided by term 2. So that's a quarter divided by a half. And if we do that, we'll end up again with a half. You can check that on your calculator. So that means we've got a constant ratio of 1 over 2. Now what we need to do to complete our sigma notation, let's get it ready here. We need our Tn that we're going to write in there. We're going to start with n is equal to 1, and we need to know what value we would write on top to complete this sigma notation. Okay, so let's figure out what the Tn is then of this geometric series. Okay, so that's a times r to the n minus 1. The a value there was 1. R we've worked out to be a half to the n minus 1. And so that I can simply write as a half to the n minus 1. Or if you wanted to, you could even write this as 2 to the negative 1 and then to the n minus 1. And then you can multiply that in. So 2 to the minus n plus 1 would be an option there. And let's have it like that, minus n plus 1. Okay, and now I need to know where are we going to end off. Okay, so then what we do is we go and we have a look at our last term. But have a look at the question here. They never gave us a last term. They just showed that it carries on indefinitely. And so that actually makes our lives very easy because we can simply say this is going to be a sum to infinity. Okay, when am I allowed to have a sum to infinity? I'm allowed to have a sum to infinity when r is anything between minus 1 and 1. And if you have a look at the r value that we got, it's a half. A half is definitely bigger than minus 1 and definitely smaller than 1. So there we have our sigma notation, the sum from the first term all the way up to infinity, 2 to the minus n plus 1. Or if you left it as a half to the n minus 1, that is also perfectly acceptable. Let's have a look at an application question. So show that the sum of this here series up to infinity represents a convergent geometric series. Okay, so convergent means we're looking specifically for that r value. Okay, we are going to need to just substitute in some values of k then. So let's do that. We're going to say, first of all, k equals 1. So it's always helpful, even if you don't know where to go, start by substituting in what you've got. So we can substitute in a 1, so it's going to be 4 multiplied by 3 to the power of 2 minus 1. Then plus our second term would be 4 multiplied by 3 to the power of 2 minus 2, the next one. 4 multiplied by 3 to the power of 2 minus 3, etc. Shall we do one more? 4 multiplied by 3 to the power of 2 minus 4 plus dot dot dot. Okay, it's going to infinity, so we don't need to carry on further than that. So that ends up being 4 times 3 to the power of 1 plus 4 times 3 to the power of 0 plus 4 times 3 to the power of minus 1 plus 4 times 3 to the power of minus 2. So we're just neatening up our exponents there. Okay, and now they want a convergent geometric series. Okay, so that means we are after the r value in this case. So r is equal to term 2 divided by term 1. Okay, so 4 divided by 4 times 3. Okay, what happens there is we end up with 1/3 as our r value. Okay, I always like to check that, especially if they want me to prove that it's geometric. Let's just check that the r is in fact a common ratio. So term 3 divided by term 2. Let's try that out. So it's going to be 4 times 3 to the minus 1 over 4. The 4's will cancel. And then we end up with 3 to the minus 1. And if we remember our laws of exponents, that is also a third. Okay, now how do we know if something is convergent? Convergent, the theory is that the r needs to be bigger than minus 1, but smaller than 1. And so therefore we can say, since 1 over 3 is bigger than minus 1 and smaller than 1, the series converges. Now here's a follow-up question. They're saying if you start at p and you add all the terms together, so in the previous one we were starting at 1, it's the same general term though. If you add them all up and you end up at 2 over 9, determine the value of p. In other words, what was your first term when you did that? Okay, so what we know from the question we just tackled is the fact that r is equal to 1 over 3, and this is a convergent geometric series. We've just proven that. We also know this formula, sum to infinity is equal to a over 1 minus r. Okay, and we've got our r value. In essence, we want to know what the a value is, because our first term would be the one where we substitute in a p. So if you can picture that with me, the first term then is 4 times 3 to the 2 minus p. Okay, so let's substitute that in, and what we know is that it's going to equal to 2 over 9. So our first term, 4 times 3 to the 2 minus p, over 1 minus a third. Okay, and now we just need to solve. So 2 over 9 is equal to 4 times 3 to the 2 minus p, over, that's going to be 2/3. Okay, so what I'm going to do is I'm going to simply cross multiply, and that's going to help me get rid of this fraction very quickly. So 2 multiplied by 2 over 3 on the one side is equal to 9 multiplied by this term here, 4 times 3 to the 2 minus p, on the other side. So if ever you are dealing with one fraction on each side, this is definitely a quicker way to deal with it. Okay, now we just need to try and solve. Let's move this up here. So we get up with 4 over 3 is equal to 36. If I multiply that, 9 times 4, 36 times 3 to the 2 minus p. Okay, now let's divide both sides by 36. Just what we're trying to do is we're trying to get p on its own, or at least the base that contains p on its own. Okay, so in the calculator, we type in there 4 over 3 divided by 36. So we get 1 over 27 is equal to 3 to the 2 minus p. Okay, and then if I want to write this in prime basis, I can rewrite this as 1 over 3 to the 3, because 3 times 3 times 3, that gives me 27. Okay, which I can then move out of fraction form, so 3 to the minus 3. Okay, is equal to 3 to the 2 minus p. And now I'm allowed to drop those bases, so minus 3 equals 2 minus p, and now it's easy game. P is equal to 5 as a final answer there. So what we needed to do was simply apply the fact that we knew the r value, we knew that it was a convergent geometric series, so we could work out the sum to infinity. We then substituted in the p so that we could have an a value, and then it became an exponential equation to solve.